Hello. So this talk is a survey of a circle of ID that has been developed over the last 20 years in harmonic analysis to extend things like Calderon-Zygmund theory and Littlewood-Paley theory in such a way that they become relevant in the study of rough partial differential equations. Now, rough can mean a whole range of things. Typically, I mean roughness of a stochastic term, something like a Brownian motion driving the equation, or I mean roughness of the media, something like L-infinity coefficients of the differential operators that appear in the equation. Now I'm going to start the talk with a very vague and general description of what this motivation is. So think of an equation that you could formally write as d of ut equal L of ut dt plus f of t dzt. And the meaning of that, well, will depend on the context, right? It could be a weak formulation of a PDE, it could be a mild formulation of an OD or an SD in a Banach space, it could be something else. It could be like a rough pass definition, for instance, that depend on what you mean by dzt. Now, how you construct the solution, what is the meaning of the equation, even that's not really the point of this talk. This talk is about techniques in harmonic analysis that allow you to derive a priori estimate on the solution. So I'm going to tell you about the techniques to do that. What do I mean by a priori estimates? I mean a control of the norm of the solution in some solution space by the norm of the data and the norm of the driving force F. So let's just think that you write your solution as something like a free evolution, so say a semi-group applied to the initial data plus an inhomogeneous term, which is something like the convolution of the semi-group with the driving force. And the questions you're asking is, one, do we have continuity of the map that sends the data to the solution? And second, do I have continuity of the map that sends the driving force F to the solution? And that's inappropriate spaces. So you're really asking for spaces of solutions, X, and spaces of data, such that these maps are continuous. And we'll show you techniques to prove the continuity of those maps. But before I do that, we should pause for a second and ask ourselves, what makes a good pair of spaces X and Y? In what sort of function spaces should I be looking for solutions? Now, that very much depends ultimately on the nonlinear equation that you're trying to solve or that you're building techniques towards solving. So there's at least three objectives you can have. The first one, which is the one that I'm mostly going to ignore in this talk, although the techniques of this talk do apply to it, is the objective of having as many drivers as possible, or more precisely, you have a certain particularly problematic driver in mind coming from your nonlinear equation, and you want to try to solve that. So that happens when you have an equation where the nonlinearity and the driver interact in such a nasty way that you cannot even make sense of their product as distribution just abstractly. You have to give meaning to that as part of your solution theory. Now, this is really the realm of regularity structure theory and recent work of Martin Eyre that has given meaning to a whole range of equations of that nature. Now, if that is your problematic, and that's the problematic of singular RPD or SPD, then the function spaces X and Y in which you want your a priori estimates are going to be naturally constructed as part of your theory that gives meaning to the equation and construct a solution. Now, there will be harmonic analysis involved in that of the kind that is described in this talk, but there will be obviously some constraint because your spaces will be adapted to the specific driver that you have to deal with. Nevertheless, there's also some freedom. In the literature, you'll see mostly spaces that are modeled on the classical C-alpha spaces of Hölder continuous function, but you can make variants of that and do things that look more like LP or Bezoff or Triboli-Zorkin spaces. Notice that in the work of Frédéric Bernicot and Ismaël Bayel recently, there's a very good example of how the theory that I'm talking about today can be applied in this sort of context. But that's not the main purpose of my talk at all. Now, the second objective you might have, let's say that your equation makes sense, you even have a solution in some spaces. What you might want to do next is have as much information as possible on the solution. And that means having the best possible space X of solutions. Now, often the question, if it's a parabolic problem, will be a question of regularity. You want to know how much regularity in space or time or mixed space and time you have, and there's a certain level that you know is the maximal you can get, and you're trying to prove an estimate with this maximal level of regularity. Now, if it's a dispersive problem, you might have different issues, right? You might want to prove Strickhart's estimate and get optimal integrability with respect to all of your variables. But the principle is always the same. You're trying to find a space X of solution that best captures the information you want about your solution as you move towards the nonlinear problem. Now notice that whether your objective is 1, you want a lot of drivers, or your objective is 2, you want the best possible information on the solution, it is all about the space X. The space Y is kind of an afterthought. Once you've found the space X in which you can solve and have a good relationship with the driver, you just define Y to be the space of all those data such that the free evolution term ends up in X. But this being said, you might still want to handle as many data as possible. Even within objective 1 and objective 2, you might have a choice of spaces X in which you can solve, and then you might try to pick the one that gives you the most data. So that is objective 3, try to optimize the data space Y. There's plenty of famous examples of that. One of my favorite one is Cortataro's result on Navier-Stokes equation. So for the Navier-Stokes equation, it's a very specific nonlinear problem, and people have known for a long time what are the right spaces X and Y in which you can passively solve. And in the early 21st century, Bourgain proved that in the space X that corresponds to the largest space Y, the problem is actually ill-posed. And then Cortataro proved that if you just go one level below, then the problem becomes well-posed. So they've identified the best possible, the largest possible set of data, and there's a space X of solution that corresponds to it. Now this is interesting in relationship with objective 2, because if you look into the proof, there were classical results on Navier-Stokes involving a space X that's built on LP and LP data, and what Cor and Tataro do is that they treat BMO-1 data, and in order to do that, their regularity estimate for the linear part doesn't happen in LP, like in the more classical result, but happens in something called the 10 space T infinity 2. We'll talk about that a little bit more later. And you've got other famous example. One that comes to mind is Burke and Svetkov, beautiful work on randomized data for dispersive equation. The idea there is that, again, you have a family of possible spaces of data. There's a certain threshold of regularity. Above that threshold, you have well-posedness. Below that threshold, you have an ill-posedness. But if you're willing to change slightly your notion of well-posedness, you can put a probability measure on a space of data that is bigger than the largest one in which you have deterministic well-posedness, and almost surely for almost all data, you're going to have a well-posedness in a almost sure sense of the equation. So with all these motivations in mind, I now want to tell you how in this variety of spaces you could choose from, you can prove continuity result answering question 1 and question 2. So let's start with the free evolution in the simplest possible case. I'm going to be looking at the heat equation, and I'm going to take L2 of RD as my space of initial data. Now, the classical Littlewood-Paley decomposition in that context tells me that an arbitrary element of L2 can be written as an almost orthogonal sum of Littlewood-Paley pieces, which are localization of the Fourier transform of U0 to a dyadic annulus. The way you implement that in practice is you take a compactly supported C-infinity function, which is 1 on an annulus and 0 slightly away from that annulus, and you use these Fourier multipliers to localize your Fourier transform. Now, this is really the same as using the functional calculus of the Laplacian, because it is given exactly by those Fourier multipliers. I've written that using a discrete sum to help understand what this all means, but a bit of a Plancherel argument will convince you that you can also do it just as well with a continuous sum. And if you do that, you could also swap your cutoffs that are compactly supported for cutoffs that are not compactly supported, something such as this Fourier multiplier, which is the Fourier multiplier by square root of t mod xi exponential minus t mod of xi squared. Right? This Fourier multiplier is roughly 1 when t times xi squared is roughly 1, and it's close to 0 when t times xi squared is close to 0 or close to infinity. So again, using Plancherel, you can prove this equivalent, and you should think of that as a smoothed out, continuous version of the Littlewood-Paley decomposition. Now, in L2 also, just Plancherel will tell me that multiplying by square root of the Laplacian or multiplying by the gradient is the same thing. So this suggests something for the solution space of my heat equation. Indeed, what we're saying is that the norm of the gradient of the solution in L2 of R plus cross RD is equivalent to the L2 of RD norm of the data. So if your space of data is L2 of RD, then a very good choice for your space of solution is the energy space of those distribution, which gradient is in L2 over space and time. Now that is a quintessential example of a general principle. When you choose a solution space X, in a sense what you're doing is you're choosing a certain way of summing up your Littlewood-Paley pieces. So a choice of X imposes a choice of Y through the Littlewood-Paley characterization of your space Y. And this is a bidirectional arrow here because you could also start with a space of data that you want to analyze, look at its Littlewood-Paley description, and this will tell you what norm you should put on your solution space. Now we're going to see how this philosophy can be extended beyond Fourier multipliers and the Laplace operator. Now the name energy space comes from the study of equations associated with an energy form. Example, you can look at a non-autonomous parabolic problem with L-infinity coefficient in space and time, and Jacques-Louis Lyons in 1957 has shown that such equation will always be such that the L2 norm of the data is equivalent to the norm of the solution in the energy space. So you should think of that as a version of the Littlewood-Paley inequalities that we saw on the previous slide, adapted to an equation which is non-autonomous and has completely rough coefficients. Now, an abstract version of that was obtained in 1986 by Alan McIntosh when he showed that this type of Littlewood-Paley estimate holds whenever an operator L on a Hilbert space has a bounded H-infinity functional calculus. So you can think of that as a version for an abstract parabolic autonomous problem of the energy estimates of Lyons. And again, this gives you a Littlewood-Paley decomposition even in contexts where the coefficients of the operators can be quite rough. Okay, we now have good Hilbert spaces X and Y of solutions and of data, but what if the spaces I really want are not Hilbert spaces? Well, then I can use extrapolation, which is a technique that tells you that if you have an integral operator that is bounded at one point of an interpolation scale, under conditions on its kernel, you can extrapolate the boundedness to a range of interpolation parameters. Now, I can think of at least three ways of doing that. One goes back to the 60s and to Calderon and Zygmund. You use the Calderon-Zygmund decomposition and the boundedness of your operator at one point of the scale to prove a weak type 1-1 estimate, and then you interpolate between this weak type 1-1 and the strong type result that you already have. The second one comes from the 70s and Pfefferman and Stein, and you prove also an endpoint estimate, but use something like an H1L1 estimate or an L-infinity to BMO estimate, and then interpolate from that. And the third one I can think of is Ruby de Francia in the 80s, where you prove at one point, maybe the point where you already have boundedness, a weighted estimate for a whole range of weights, and then you extrapolate that to a boundedness for a whole range of values of P and a whole range of weights. Now, the point that I want to make in the coming slides is that if you look at the information on the kernel that allows you to run any of these methods, this is always an information of an off-diagonal nature on the decay of the kernel. So what do I mean by that? I mean that I'm dealing with operators that have so-called off-diagonal bounds. Now, what it means is this estimates, and the way you should interpret it is that you start with a function that is supported in a set capital F, and then you apply the operators TT, and you look at how much of the norm of that function can be found in a set E. And the idea is that if your TTs are integral operators with a singularity on the diagonal and decay away from that singularity, quintessential example being the heat semi-group, then what is going to happen is that you're going to have a decay of this quantity that depends on the distance between E and F, increase with the distance between E and F, and increases if you send T to 0. And there's a scaling factor here that correctly accounts for the fact that obviously if all these operators were the identity, they could not possibly map LQ0 to LQ1 unless Q0 is equal to Q1. Now this property certainly captures decay properties of integral operators, and it does that without having to explicitly refer to their kernel. But if you think of the extrapolation theories that I was just mentioning, usually you don't just use decay of the kernel, you also use some smoothness of the kernel by combining it with some cancellation properties, like cancellation of the bad parts in the Calderon-Zygmund decomposition or cancellations of the atoms in the Hardy space H1. But the problem is, if you're going to go towards rough equations, you're going to have kernels that are not smooth, and you're going to have situations where you don't have the analog of the cancellation properties. So can you run extrapolation arguments without relying on smoothness and or cancellation? Well, yes, this was realized in a breakthrough paper of Zong and McIntosh in 1999. They managed to prove weak type 1-1 estimate under less demanding assumption than the amount assumption without really exploiting smoothness and without exploiting cancellation in the Calderon-Zygmund decomposition. These ideas were then extended by Blunk and Kunzmann in 2003, realizing that there was very much a principle behind this breakthrough result of Zong and McIntosh. And then a little bit later, starting in 2004 and 5, Pascal Aucher really saw the power of that method and started applying it to a whole range of harmonic analytic and PDE questions. So how does the method look like? Well, the idea is that you need to choose an approximation of the identity that has appropriate off-diagonal bounds. If you're in a classical situation, you could put just average of the balls, or you can put a heat semigroup in order to have that. But if you are in a more complicated situation, you can tailor your approximate identity to the situation that you are dealing with. And now the replacement for a cancellation plus smoothness condition, so typically you use that to improve the decay of the kernel, is the fact that your operator t, if you multiply it by I minus AT, as good off diagonal decay. But again, this is better than having to exploit smoothness plus cancellation, because you can encode that in an operator AT that you manufacture. So what can you get from this extrapolation methods? Well, you can get R bound in LP as long as you have LQ not LQ1 of diagonal bounds and your P is between Q0 and Q1. You can also get a bounded H infinity calculus in LP as long as you have it on L2 and your semigroup in complex time as appropriate of diagonal bounds. So what does this tell us about our question 1? Well, it tells us that if you have a bounded semigroup on L2 and you want to treat LP data under appropriate of diagonal bound assumptions, you will be able to extrapolate the boundedness of the semigroup to LP, get an estimate of that form, which really tells you that you can solve in the space L infinity of time with value LP in space. Now, that is not a good space from the point of view of maximal regularity. So if you want some more information on your solution, more regularity of your solution in particular, you should extrapolate, say, the boundedness of an H infinity calculus from L2 to LP. Well, you can do that too, and then the theory of H infinity functional calculus will give you estimates of that form, which you can reinterpret by saying that an appropriate solution space, if your data space is LP, is this variation on Lyon's energy space. Now, if you want to learn more about that theory, I cannot recommend enough the series of books by Thomas Hutton and Jan van Even, Mark Ferrer, and Lutz Weiss called Analysis in Banach Spaces that develop the theory in a beautiful manner. Okay, so what about question 2? Well, question 2 is the boundedness of a map such as this convolution. Now, if you're in L2, application of Hilbert space valued Plancherel inequality will tell you that as long as L generates an analytic semigroup, then you're going to have boundedness of this convolution term in L2 of, say, a finite time interval cross RD. Now, if you want to work in LP, there's a result of 2001 of Lutz Weiss that tells you that if you can prove that your semigroup is R-bounded in LP, then you're going to have boundedness of this maximal regularity operator, the operator that maps the forcing term back to L of the solution. Now, R-boundedness, as we've just seen, can be extrapolated by Per-Kunzmann result. And if you're interested in this energy space that I was mentioning just a second ago, then van Nerven, Ferrer, and Weiss have also shown that R-boundedness is enough to guarantee the continuity on that energy space of the maximal regularity operator. Again, you can get that form of diagonal bound through Per-Kunzmann's result. So we've just seen that off-diagonal bounds allow us to run a rough version of Calderon-Zygmund extrapolation technique, and that gives us our boundedness or H infinity calculus that then gives us information about our equations. But what about Rubio de Francia's approach? And this approach, the extrapolation itself has nothing to do with the operator. It's an extrapolation of inequalities, really, which boils down to properties of the averaging operators of the balls, the quintessential ATs. What has to do with the operator T and of diagonal bounds is how you check the assumptions. Check the L2 W boundedness for any W in the Mackanaut class A2. Now, the modern way to do that is through sparse domination. You dominate your operator by an operator involving averages over sparse families of cubes. And this can be done in rough settings, provided you have appropriate off-diagonal estimates. Now, these off-diagonal estimates are a little bit more demanding than what we saw for extrapolation of, say, the infinity functional calculus, but note that what you get out of them is a bit stronger too, because you get not just LP boundedness, but weighted LP boundedness. And this can be helpful in applications, either because, say, for nonlinear PDEs, you want commutator estimates, or because you want rougher data. Here is such an application. One can get maximum regularity in LP of time with value in LQ of space for non-divergence form, non-autonomous parabolic problems that have coefficients which are L infinity in time and have a little bit of regularity in space. The way Chiara Gallarati and Marc Ferrar prove that is by first considering the case of X independent coefficient, for which you have nice Fourier multipliers to which you can apply your Robio differentia extrapolation techniques, and then using PD perturbation technique to add some dependency in the X variable. This is very interesting because it reminds us that we do not need to use the harmonic analysis for all of the extrapolation. We can use it on a simple building block, and then we can use PDE methods to go further. This is very much Krylov's philosophy in approaching this type of estimates. Now let's talk about the third approach, introduced by Pfefferman and Stein in the 70s and then reinterpreted in the function analytic framework by Kaufman, Meyer, and Stein in 1985 through their introduction of 10 spaces. So 10 spaces are very similar to the energy spaces of P with value in L2 that we mentioned earlier, but they add a extra averaging over the spatial variable. The point I want to make about this method of extrapolation is that it requires less off-diagonal bond information than the previous two. Good example of that, if you want the analog of R boundedness in this context, all you need are L2 off-diagonal bounds of fairly minimal order. And if you want the boundedness of a singular integral operator above 2, again, all you need are L2 off-diagonal bounds. And if you want P closer to 1, then you need a little bit more off-diagonal bounds. So can we use this advantage of 10-space extrapolation requiring less off-diagonal bounds in PDE application? And well, the answer is very much yes. If you go back to this problem that Jacques-Louis Lyons was studying, for example, when you have L infinity coefficient in space and time, till very recently we didn't really have an analog of that if you wanted LP data rather than L2 data. And we found one, and in order to create it, what we had to do is use as a solution space the space defined by this norm using the gradient of u in TP2. And then Victoria Zaton recently extended that to higher order problems. Now, this is very interesting because hidden behind this statement, there is a full well-Posner theory, including a uniqueness theory that was very much missing, especially in the higher order case, even for smooth coefficients. Now, what about question 2? Well, in the autonomous case, at least, for a Dirac operator, the maximal regularity operator here is bounded on TP2 for all values of P's, including the endpoint. Now, that's interesting because this endpoint here, T infinity 2, the boundedness of the maximal regularity operator associated with the Laplacian is exactly what Corr and Tataro use on their Navier-Stokes result. And it's also interesting because even within the reflexive range, you can find matrices A such that L does not generate a semigroup in LP. So you have boundedness of the maximal regularity operator on TP2, and you could not possibly have it on any mixed norm LP spaces. Now, all my examples so far have been boringly deterministic. What if you want to study a stochastic integral operator of that form? Well, if your stochastic integral is in the Ito sense against a cylindrical Brownian motion, you can apply Ito isometry, and that's going to tell you that estimates of this quantities boil down to estimates of these quantities, so essentially to the extrapolation of a deterministic integral operator. Now, if you apply your extrapolation methods to this deterministic operator, you get results such as this one, a stochastic maximal regularity estimate for Dirac operators. Now, what's interesting about that estimate is that it's valid for all values of P. So if you were to use, instead of 10 space to define your solution space X, a mixed norm LP spaces, then you could not possibly get that. You would be restricted to the interval 2 to infinity, even for the Laplace operator. We can even combine all of the previous gains and treat non-autonomous stochastic SPDs. Mark and I have an example of that where we treat coefficients that are L infinity in space and time and get something like a maximal regularity estimate in 10 spaces. Now, I consider it to be very much unfinished business because what we have is not a true maximal regularity estimate. We're measuring regularity in terms of a weight in the time variable instead of using proper derivatives. Nevertheless, this is a proof of concept that something can be done without assuming any regularity in space or time. Now, of course, there is a catch to all of that. If you use the Pfefferman-Stein approach to extrapolation with 10 spaces, then you need less off-diagonal information, but you also get less information on your solution. You only know it's in the 10 space. In some cases, this is all you can possibly hope for, but in better situation where you have better off-diagonal bounds, then you can use a Calderon-Zygmund approach or a Robio differentia approach and get more information on your solution. A perfect example of that is the recent work of Émile Lorist and Marc Ferrat, where they look at solution spaces like LP of time with value on LQ of space. They start, like we did in the 10-space case, with Ito isometry to reduce the problem to a more deterministic question, but a question involving norms in gamma spaces. And then under strong enough of diagonal bond assumption, something expressed as a remainder condition here, they prove an extrapolation result. Now, this extrapolation result can only work in the range 2 to infinity. I've stated here as an extrapolation upwards, but they also have an extrapolation downwards. Interesting point about their proof, they also use these ideas of Zhong and McIntosh to bypass the use of cancellation conditions that you could not exploit here. And this has also very interesting SPD applications. So to summarize, we've talked about 3 approaches to extrapolation: Calderon-Zygmund, Pfefferman-Stein, and Rouvier de Francia, and we've seen that they all have rough analogs using a varying level of diagonal information. If you use the Pfefferman-Stein approach in 10 spaces, that's where you need the least amount of input, and therefore it works in the most general situations. But on the other hand, you get the weakest output, namely you only get 10 space information about your solution. If you use the Rouvier de Francia approach, on the other hand, you need a lot more input, but you get a much more satisfying output because you get not just mixed norm LPLQ estimate, but even weighted LPLQ estimates that are very helpful.